So to really introduce logarithms, I'm going to go back to another exponential function. We'll get away from e base for just a second. Another very common base in science and chemistry and stuff is base 10. So I want to look at this function. So this is not a logarithm. This is just an exponential function with a base of 10. And if I tried to plot some points, it's kind of easy. -2, -1, 0, 1, 2. I can plug in these exponents and plot some points. Let's start in the middle, if you would. If you plug in a 0, 10 to the 0 is 1, of course. Anything to the 0 is 1. If you plug in a 1, 10 to the first is 10. If you plug in a 2, 10 squared is 100. This is how this works, of course. When you plug in a -1, 10 to the -1 is 1/10. That's how it works. A -2 is 10 to the -2. You can even use a calculator, but you should actually know that it means this, which is 1/100th. If I plot these points on a graph, it's just classic exponential growth. You know, like I said, yesterday I did base 2, I did base 5, we learned about base e, so today just happens to be base 10 for a second, no big deal. It looks a lot like those other ones. Maybe it's a little steeper because it's base 10. What does it look like? At 0 it was 1. At 1 it was 10, okay. At 2 it was 100, yeah. I can't quite do that, but I can try. At -1 it was 1/10, yeah, 1/10. At -2 it was, wow, 1/100th. See, it gets small, but it never touches that x-axis, so it's this, just classic exponential growth, but very steep, very steep. There's an asymptote here, and there's a picture of good old y equals 10 to the x. All right, so guess what? I want to talk about his inverse. Now, we had a good discussion in chapter 4 about inverse functions. If I want to find his inverse, then let's see, there was a Smith method that didn't work too great all the time. There was a book method. Do you remember the book method to find his inverse?
Switch x and y.
Switch x and y. Switch x and y, and then he said solve for y. Right. You switch your x and y, and then we can try to solve for y, but y is up in the exponent, and I mean, this is what's weird. I don't have a mathematical move to do this until I invent something called logarithms. I mean, there's no mathematical move. You don't to unbase 10 something. I mean, to unbase 10 something require, the way we say that is we say let's log base 10 both sides. This is not the natural log. This would be the logarithm, L-O-G, logarithm. You know, hang on. Just switching the x and y, really, that gives you the inverse right there, actually. I mean, switching the x and y, that's the inverse. We had a habit of trying to solve for y so we could label it f inverse of x, you know. But just the switching makes it the inverse. And just switching the x and y also leads you to, you know, a new chart. And what would the new chart look like if you switch the x and y? Again, from chapter 4, it's this chart flipped is what it is. Hang on. So I'm going to do that. I'm going to flip that chart, and then I want to check out its graph. But I do want to say this. So this means, again, I'm having a hard time explaining this because I just have to solve for y, I have to kind of rewrite this as y equals the log base 10 of x. Actually, what did I just do? You could say that, so that base 10 is a little subscript on the log. It tells me the base of the log. And I guess I just took the log base 10 of both sides. On this side, I had the log base 10 of x. On this side, I had the log base 10 of 10 to the y. What happens to a log base 10 of something that has a base 10? The log base 10 of something that has a base 10 cancels each other out, and I get y. So this is what I did, and then I wrote it backwards, if you don't mind. Did that confuse you? I took the log base 10 of both sides, then I just wrote it backwards. I wrote him on this side, wrote him on this side. See, all right, hang on. Let's do this. You ready? Watch this. This will explain it better. What do you do with an exponential function? You plug in the exponents, and you do the base to the exponents, and you spit out the answers. Why? You plug in the 2, you get 100. You plug in the 3, you get 1,000. You're plugging in the exponents and looking for the answers. You know what you do on logarithms? You plug in the answers, because it's backwards. Everything's backwards. Now you're plugging in the answers, and you're looking for the exponent. Watch what happens when you plug in 100. Sorry. When you plug in 100 for x. When you plug in 100 for x, you know the answer because you're looking over here, but you're plugging in the 100 and you're asking yourself, what is the exponent that you put on 10 in order to get 100? See, that's what you have to say to yourself. Listen to that. That's a long sentence. But when someone plugs in 100, you have to say to yourself, the answer y. Y is the exponent you put on the base, which happens to be 10 in this case, to get the input x, which in this case happens to be 100. That's a long sentence, but if you can understand logarithms if you say it to yourself every time. When someone asks you, what's a log base 10 of 100, you should say, oh, it's the exponent. The answer is the exponent you put on 10 in order to get 100. It's actually kind of rhythmic. Get it? Logarithm. Logarithm. There is a rhythm to it. It's the exponent you put on 10 in order to get 100. That's what I'm saying. That is what I'm saying. It's a 2. Anyway, let me just keep playing here a second. What if I plugged in a 10? If I plugged in a 10, I'm looking for the exponent you put on 10 in order to get 10. The exponent would be 1. I'm standing in front of the chart here. Watch this. What if you plugged in a 1? That's kind of weird, but now you're looking for the exponent that you put on 10 in order to get a 1. And that exponent is 0. Good. Again, it's just all these flipped. If you plugged in a 1/10, I think the exponent is -1. If you plugged in a 1/100th, I think the exponent is -2. If you plot these points, you'll get a graph of the logarithm function. The logarithm function is kind of interesting. Let's start here. 1, 0, 1, 0. By the way, it's just the mirror image of this one, right? It's the inverse of this one. So it's 1, it's all these points flip-flopped. Let me try this. 1, 0, 10, 1. Well, I gotta go way out here to 10, and then I just go up 1. Look at this one. I gotta go way out here to 100. Look, way out to 100, and then how high do I go? 2. What happens when I go way out to 1,000? When I go way out to 1,000, the exponent is 3. See, the logarithm is like the most pitiful. It's just terrible. Oh, no, it's fine. But the exponential function increases quite rapidly. The logarithm function increases quite slowly. Quite slowly. Super slowly. Slower than anybody. This logarithm function does increase, It does not decrease. It does increase, but it increases so slow, slow, slow. You know, when I go out to 1,000,000, you know what the exponent is? What is the exponent you put on 10 in order to get 1,000,000? Maybe you don't know. It's 6. You go all the way out to 1,000,000, and the answer is 6. That's how slowly this thing rises. Oh, right here, though, it takes a huge dive. What am I doing here? When x is 1/10, it's a -1. When x is 1/100th, it's a -2. What it does is it takes a dive right here toward -infinity, and guess what? There's a vertical asymptote right here. By the way, it's that mirror image concept. It's totally that mirror image concept. This one has a y-intercept of 1. This one has an x-intercept of 1. This one has an asymptote at y equals 0. This has an asymptote at x equals 0. This one increases quite rapidly. This one increases quite slowly. They're inverses of each other. They're the mirror image. Remember the mirror right here? They're the mirror image of each other around this mirror. You know, Monday or Tuesday, I spent a lot of time graphing exponential functions. I think graphing exponential functions is important to me and to you. I just showed you a graph of a logarithm function. I plotted some points. I tried to explain what it was. It's the inverse of this thing. And I just showed you his graph. Listen, there'll be a couple graph questions about logarithms, but it's not near as important to me as the graphs of the exponential functions. But there'll be a couple homework questions about this graph. You could shift it to the left or shift it to the right, or shift it to the left maybe. But I don't know. Graphing logarithm functions is not my big thing here. But understanding them and how to use them is. And I wanted you to see one good graph and see that it's the mirror image of this guy. So, look at this one then. So, if I just start throwing logarithm problems at you, they're new and strange and they can be any kind of base. This one happens to be log base 2, and it's the log base 2 of 8. And what I need to understand when I stare at this is that I'm looking for the exponent. This is the answer to this. The answer to a logarithm is this sentence. The answer y is the exponent you put on the base 10 in order to get 100. In this case, I'm looking for the exponent that you put on 2 in order to get 8. And the answer is 3. So this is 3. And it's 3 because 2 to the third equals 8. This is the exponential statement, and this is the equivalent logarithm statement. And what they often do, and what can be helpful to you, is they teach you how to rewrite logarithms. So when they give you a log, so I just asked you to figure this one out, and you all did good. You did it. But what they often ask you to do is they play this game. Can you rewrite this stuff? So here's one. Here's one. By the way, what's the answer to this? It's the exponent you got to put on 4 in order to get 16. Thank you. Okay, there's the answer. But besides finding the answer, they'll ask you to rewrite it in exponential form. So here it is in logarithm form. Can you rewrite this statement in exponential form? And you would start with, I think you should start with the base. Who's the base? 4. And you would raise that base to the exponent, which is the answer to a logarithm is the exponent 2. And then it equals what's inside the logarithm, 16. And that little step is handy and helpful at times. It's called rewriting the logarithm. And you got some homework that they don't even ask you to do logarithms. They just say rewrite some logarithms. just to get you used to this relationship. 4 to the 2 equals 16. That's what this says. If you were trying to figure one out, like watch this one, log base. Watch this one, log base 4 of 32. So I'm trying to figure this out. This is a little subscript down here. It's a subscript on the logarithm is what it is. The 32 is the input to the logarithm, and then we're looking for the answer. And the answer to the logarithm is always an exponent. And so this one's not as easy to figure out. But so maybe what you do is this. Watch, here's a sort of a technique for figuring this out, is you call the answer like this unknown x or y, let's call it y, and then rewrite it. So if you rewrote it, what would you do? If you rewrote it, what would you write?
4 to the x equals 32.
Okay, good, except I called it y. But 4 to the y equals 32, yeah, all right. So now you rewrote it. It might help you think about it. It's still not a nice number. That 32 isn't real nice, but I mean, and then you know what I would do? See, I would start guessing. See, especially since it's a 32, I would say, well what's 4 squared? 4 squared is 16. That's not it. What's 4 cubed? 4 cubed is 4 times 4 times 4. I know, I can pick up my calculator. That's 64. So it's not, okay, so it's got to be something in between that. How do I get 32? So the exponent doesn't have to be a whole number, of course. The exponent can be somewhere between 2 and 3. Maybe 2.5. And maybe I would just try that on my calculator. What is 4 to the 2.5? And I would get 32. And then so that's the answer, 2.5. But I sort of just guessed, right? I mean, I used a little logic, and then I narrowed down my guess. Something between 2 and 3.
Can you do like 2 square root 8 or something like that? Would that like you know what I'm trying to say?
I don't know what you're trying to say. You're trying to change the 32 to 4. It's like a 4 times 8.
That's what could you do something like that?
You could maybe do something. You're right. I think you're on to something. Now, so I kind of prefer this guessing approach. She is on to something, though. You know what they do? Here's what they do. Yeah, I've almost forgot to teach this. Because this is kind of smart. This guessing approach is kind of smart. But there is a method, because sometimes students don't like guessing. They think that's weird. There is sort of a method. Check this out. The method is try to get the base the same. So let's play around here a second. You happen to know that 32 is 2 to the 5th? Did you know that? Maybe you didn't know that. But 32 is 2 times 2 times 2 times 2 times. It's 2 to the 5th. It's 2 to the 5th. A 4 is a 2 squared. So check this out. This is 2 squared raised to the y. Hey, what do you do when you have exponents raised to further exponents? Do you know the rule here? You multiply those. So this is 2 to the 2y equals 2 to the 5th. So here's the strategy to solve this. If you don't want to guess, the strategy is try to make the base the same. And if you can get the base the same, then you can just drop the base. I mean, if 2 to the 2y equals 2 to the 5th, let's just drop the 2's, and apparently the 2y has to equal a 5. And if you divide by 2, what's y? 5 halves, which is 2.5, which is what we guessed 3 hours ago. No, a couple minutes ago. So there sort of is a strategy. I don't know. In recent years, I used to teach this. I guess in recent times, I've kind of gotten away from teaching this. I've kind of just guessed, maybe. I'm not sure how helpful this strategy is, but it works. It's a strategy for solving. You guys, one big point here then is What is a logarithm? I mean, when you leave here today, what's a logarithm? It's the inverse of an exponential function. It's a function, logarithm function. I mean, there's a lot of things you can say, but I want to say this. A logarithm is, I mean, this is a logarithm, and the answer to a logarithm is, and so a logarithm is an exponent. I mean, ultimately, it's that sentence that I lost, but that sentence said, the answer to a logarithm is an exponent. It's the exponent you put on 2 in order to get 8. A logarithm is an exponent, is what it is. A logarithm is an exponent. Like I said, log base b of a equals x. I mean, this is strange, but can you rewrite this logarithm? Can you rewrite it? How do you start? Who's the base? The b is the base, yeah. So the b is the base. Who's the exponent? Yeah, the answer to the logarithm is the exponent. The answer to the logarithm is the exponent. And then that base raised to that exponent gives you what's inside the logarithm. I mean, this is called rewriting the logarithm in exponential form. Rewrite. It's a good little tool. So there are all kinds of logarithms. Listen, there's this, but in science, and we use this. They use this for they use this log base 10. So log base 10 is a very famous logarithm when it's base 10, and it's used for pH in pH formulas in chemistry. It's used for the Richter scale for measuring earthquakes. They use logarithm log base 10. And log base 10 is so common, I think sometimes they call it the common logarithm. And because he's so common, and they didn't used to do this when I was a kid, but nowadays they say, you know what, you don't have to write the little 10. If just write LOG, if you write LOG, we know it's base 10. Okay, we know it's base 10. You don't have to write the little 10. When I used to learn this stuff in kindergarten, my kindergarten teacher would never let us take off the 10. She said, you have to write the base. I mean preschool, sorry, it was preschool. 3-year-old preschool. Anyway, here's another one. Log base e of x. Well, I introduced you this today, and nobody writes log base e of x. When it is log base e of x, when the base is e, that's a famous one, we call it the natural logarithm. And we don't write the base, and we don't write log, we write ln of x. So I already kind of told you that today, but I never wrote it like that. So these are two real famous logarithms, and your calculator should have a button for both of these. You probably have a button for this and a button for this on your calculator. Can you find, let's just see, can you find those buttons and use them? Can you do the ln of 842? Can somebody just tell me the ln of 842? Just checking, just to see if you can use your buttons.
6.74.
What did you say?
6.74.
Say it one more time.
6.74.
Thank you. 6.74. Good, okay. One more decimal, please.
Or 3.
3, okay. Thank you. Now, wait a minute. Why is that the answer? Because if you took the base, what's the base? What's the base?
10.
No.
E.
E. E. If you took the base, E, and raised it to the 6.743, guess what you should get? 842. I mean, we're looking for the exponent you put on E in order to get this number. So I'm just double checking this. Now try this if you would. Try this on your calculator and tell me what it says. That means you got to find your E button, which is different than your log button. They're inverses of each other. They might be the same button. One of them is second, one of them is, I don't know. You got to use your second feature maybe. But now tell me what this is. It should be 842. What is it?
848.1.
Holy, really? It's that far off? It's 848.1? Is he right? All right, that's interesting. Can you tell me why it's off? I mean, how come this isn't perfect?
I think the L in 842 is wrong. I think it's supposed to be 6.735.
Oh.
Yes, it is. It is supposed to be 6.735.
Okay, all right, so something happened to him on this. You know what? He might have not have used his LN button. Maybe he used his log button.
Well, I think he rounded up to a 4.
Or he just rounded a little different. All right, I didn't hear him too well. All right, let's try this again. The LN of 842 is?
Is 6.735.
All right. And that's rounded to 3 decimals.
Oh, then that would be 6.736.
Okay, thank you. All right, rounded to 3 decimals. I'm getting picky, ain't I? All right, now, if I put that in here, I want to see what happens. 6.736. See, it won't be that far off, but it's still going to be a little off. I'm trying to make a point here. Try this for me and tell me what the answer is.
842.1852.
842.1852. So how come it ain't exact?
I got 185.
But how come it's not this? Do you know the answer? It's pretty obvious. I think you know.
Because your exponent wasn't exact on the button.
Because this was rounded.
Right.
Thank you. We rounded this answer, so when I go try to check this answer, it doesn't come out exact. Because this answer's been rounded. That's what I want you to understand. Right? Does it make sense? Okay, thank you. Let's try this. Can you use your log button to do this? Watch this. LOG of 8482116. Now wait a minute. Don't tell me the answer yet. I'm gonna see if I can figure it out. Watch me. Without a calculator, the brilliant, amazing Smithini. You ready? Watch this. So, what's the base on this one? 10. Okay, it's base 10. Thank you. So now, let me think. I'm looking for an exponent that gives me this answer. I'm looking for the exponent. If you put it on 10, it gives me this answer. Now watch me. So do you think it would be 10 to the squared? No, I don't think so. You think it would be 10 cubed? That would be no, I don't think so. 10 to the 4th? 10 to the 4th is 10,000. You know, it's a 1 with 4 zeros is what it is. Anyway, no, it's not 10,000. Let's see, but 10 to the 5th would be 100,000. Nope. Let me jump down here. 10 to the 6th would be 1,000,000. Actually, it's, okay, this is 848,216. So I'm thinking the answer is somewhere between 5 and 6. I'm looking for an exponent somewhere between 5 and 6. Probably closer to 6. This is the great Smithini. It takes a while, but eventually you might get it. I'm going to say, now the great Smithini just totally gets in touch with the universe and whatever. I'm going to say it's this. But that's me guessing. Am I right? Pretty close? All right. To really do it, you just pick up your calculator and you punch in this and you hit your LOG button. And what is the real answer?
5.929.
Okay, thank you. 5.929. Ah, the great Smithini. A loose connection. Cool. But what am I trying to do? I mean, you know, I was asking you to punch buttons on your calculator, so that's not too exciting. And also, when you do that, you can kind of lose grip of what does it mean. So, besides punching buttons on your calculator, I'm trying to make you think about how you can kind of figure it out. It's somewhere between 5 and 6 is what we figured out here. So there's some common sense you can think about here. So there's these two very famous logs. They have these names, and there are buttons on your calculator. But then there's others logs. I mean, can you do this? The log base 17 of 1. Can you do this? The log base 2 of 32. Can you do the log base 3 of 9? You know, can you do the log base whatever? Anyway, guess what? So now I don't have a button on my calculator. I do not have a button on my calculator, so by the way, I used to say that. I used to say you don't have a button on your calculator for these. The truth is, you might. Nowadays, these calculators have caught up to me, and they might have this third option. I told you that you got this option and this option. You might have a third logarithm thing that says that allows you to type in any base you want. I was kind of hoping you didn't, because I want to make you do some of these things in your head without a calculator, because I think it helps you understand them. I mean, again, you're looking for the exponent that you put on 3 in order to get 9. The answer is, thank you. You're looking for the exponent that you put on 2 in order to get 32. And the answer is 5. I mean, you can kind of use your calculator backwards to figure that out, but I'm trying to tell you, you don't have a log base 2 button. What about this one?
0.
Oh, 0, because anything to the 0 is 1. Yeah, good. Good. So good. We can do some without a calculator, maybe. Maybe. Hey, I got 3 minutes. I might want to say something else here, just right at the end. This is quick and fast here, but there's these, I'm still in 5.2, and there's these special properties of logarithms. And here they are. So this is true for any log. I think I'm going to just use ln for my example, but it's true for any log, base 10, base 2, base 3. And here's the rule. It says if you have the log, the ln, by the way, when I read ln, I say log. It's a logarithm. It's the natural logarithm. Or it's a logarithm au naturel. Maybe that's what it is. But anyway, it's a log. The log of an a times a b, this is kind of interesting. You're allowed to bust this up into the log of a plus the log of b. Now that's really kind of trippy, man. Math doesn't usually do stuff like that. You don't do that with other math. You don't take a product and turn it into addition. I mean, these are special log properties. Here's another one. By the way, after you read this one, you probably know this one. If you are dividing 2 terms inside the logarithm, you could bust it into 2 separate logarithms, and what would you do? Subtract them. Yeah, you would do the natural log of the a minus the natural log of the b. It's equivalent. It's equivalent. It's a special property of logarithms. Here's another one. This is the last one. The third one is, if you have the natural log of, or any log of a number that has a power on it, I'm going to put a p for a power up there. So this is a to the p power. Then you're allowed to take that power and bring it down front and multiply it down front. It's a special property of logarithms. It's kind of weird. You're taking multiplication and turning it into addition of 2 separate logs. You're taking a division and making it subtraction of 2 separate logs. You're taking raising to an exponent and making it multiplication. Now I'm saying this is weird and nothing else in mathematics acts like this. But does something act like this? Does this remind you of something?
Exponent.
He says it reminds him of the rules of exponents. Because the rules of exponents, oh, and by the way, what did your teacher say? What is a logarithm?
Inverse of an exponent.
Yeah. But in one word, a logarithm is an exponent. Look, what is this logarithm? It is 5. It is the exponent you put on 2 in order to get 32. The answer to a logarithm is an exponent. Logarithms are exponents. And he says these special properties remind him of the rules of exponents. Do you know what he means by that? That when you multiply like bases, what do you do when you multiply like bases? You add the exponents. What do you do when you divide like bases? You subtract the exponent. I mean, it's a little bit of a stretch. It's not exactly, but it's related to these ideas, yes. What do you do when you have an exponent raised to another exponent? You multiply. So these rules of exponents are connected to these properties of logarithms. I think it's time for me to quit. Thank you for listening. Thank you for listening and trying to learn. I think I'm through 5-2, but there might be some stuff you can't quite do in the homework.